So now on to our last topic in discrete mathematics, and that's probability. Before we can actually talk about probability, we have to talk about combinatorics or counting, and a couple of principles and rules that guide counting. Starting with the fundamental counting principle, which pretty much everything else is based off of. You already know the fundamental counting principle, but here's the fancy schmancy way of saying it. It says let E1 and E2 be two events, and an event can be like drawing a card from a deck or rolling a number cube. And we're going to say that E1 can occur M1 ways, and then after E1 has occurred, E2, which is a separate event, can occur M2 different ways. And if I want to know the total number of ways both events can occur, all I have to do is multiply the two number of ways they can each happen. And this, of course, can be extended to more than two things. So I can have, 20 events, and all I have to do is multiply each of the number of ways those events can happen. And so this principle here guides pretty much the rest of this lesson. Now on to the examples. So, very basic level example. How many two-digit whole numbers are less than 80? And so in order to figure this out, I have to think about the possibilities I have for each digit. And the way I like to do this is to make two little cups, and inside the little cups will go the number of ways things can happen. So if I'm looking for two-digit odd whole numbers that are less than 80, then I have a certain number of options for that first digit. And so that first digit can be, 1 through 7, which gives me 7 possibilities. And it has to be odd. And in order to be odd, a number must end in 1, 3, 5, 7, or 9, which is 5 different numbers. Now, it's not 75 different two-digit numbers, because that makes absolutely no sense, but it is 7 times 5, because the fundamental counting principle says I just have to multiply the two number of outcomes. So event 1, in this case, was the tens digit, and event 2 is the ones digit, which gives me 35 numbers that are odd and less than 80. And that's how we use the fundamental counting principle. Basic enough, yes? Now, of course, we have to complicate things, so let's talk about these things called mutually exclusive events. And mutually exclusive means either one is going to happen, but not both at the same time. And I'll show you an example to make that really clear in a second. But there is an additional rule that goes with the fundamental counting principle, and this is called the additive rule. It says if the possibilities being counted can be grouped into mutually exclusive cases, then the total number of possibilities is the sum of the number of possibilities in each case. So take a second, pause, write that down, and then we'll do the example. So how many odd whole numbers are less than 80? Okay, so this, I could go ahead and count all the numbers up, but I don't want to do that. I'm going to think about, what kind of numbers do I have that are less than 80? I can have two cases of numbers. Case 1 are one-digit numbers, and case 2 are two-digit numbers. And these two cases are mutually exclusive, because if you think about a number, you are either going to be one-digit or two-digit if you are going to be less than 80, correct? So then I just have to figure out how many one-digit numbers there are, and then how many two-digit numbers there are that fit these criteria, and then I just add them together. So in this case, there are only 5 one-digit odd numbers, and from the previous example, I had that there were 35 two-digit odd whole numbers. And so then, because of the additive rule for mutually exclusive events, I have two mutually exclusive cases, the case of the one digits and the case of the two digits. So to find the total number, all I have to do is add these two together and get 40. Now let's think about this more complicated example. How many 3-character passwords using digits and vowels can be made using at least one vowel in each case? So I have to break this up into mutually exclusive cases that I can then find the individual numbers and then add them up. So I have the case of one vowel, I have the case of two vowels, and then 3 vowels. Now I know the vowels are A, E, I, O, and U. We're not going to go for those special sometimes vowels, just the straight up A, E, I, O, U. in which there are 5. And then I also know that there are 10 digits. And so then I just have to think about the different cases. So if I have case 1, one vowel, I can have the vowel first and then my 2 digits. So I have 5 choices for the vowel and then 10 choices for the digit and then 10 choices for the digit. But this is a password, so order is going to matter. And then so I can have the vowel be in the middle, or I can have the vowel be in the end. And then if I think of the case of 2 vowels, they can be both in the beginning, they can have the digit in the middle, or they can both be at the end. And in the case of 3 vowels, well, those are the options I have. I have 5 choices for the first vowel, 5 choices for the second vowel, 5 choices for the third vowel. And so if I multiply all these individual cases together and then add them all together, I will get the answer to this question. So one of the fundamental questions of counting or combinatorics is whether or not order matters. So we're going to look at the case of where order matters first. And order matters when we talk about these things called permutations. And a permutation of n different elements is an ordering of the elements such that there is a first, second, and third place. That means order matters. So what I put in the first position makes a difference because that's the way permutations work. And the way to calculate those is to think back to the fundamental counting principle. If I want to arrange all n elements, then what I have are n little cups, and I have n options for the first cup, and then 1 fewer option for the next cup, and then 2 fewer for the next cup, so on and so forth, until I get down to only 1 option for the last cup, which of course gives us n factorial. So if I have n things, and I want to figure out how many different ways there are to order them, so that of course order matters, then I have just n factorial. Now if I want to find the number of permutations not of all n elements, but just r of them, I have this thing here, which means permutations of n things taken r at a time. And that's really just n factorial over n minus r factorial, or n times n minus 1 times n minus 2 dot dot dot, n minus r plus 1. This example asks, what is the number of permutations for the letters A, B, C, D, E, and F? And I just have to know, well, how many elements am I permutating? And I have 1, 2, 3, 4, 5, 6. And so that means it's 6 factorial, or 720 permutations of the letter A, B, C, D, E, and F. And if you forget the formula, then remember the fundamental counting principle. And you can think of it as, well, I have 6 spaces I need to fill. I have 6 options for the first space. Once I chose that first letter, I only have 5 left. And once I choose that letter, I only have 4 left. And once I choose that letter, I only have 3 left. And once I choose that letter, I only have 2 left. And then I only have 1 choice for that last letter, which is where 6 factorial comes from. Now, what about this problem? If 8 horses run a race, how many different ways can the horses come in first, second, and third? No ties. You can realize that, hey, order matters, so therefore I'm talking about a permutation. And so what you're looking for is a permutation of 8 items taken 3 at a time. And you can just use the formula, which says this is going to be 8 factorial over 8 minus 3 factorial. And then you get 8 times 7 times 6 times 5 factorial. Those cancel off, and you're left with, I believe, 336. Now, if you forget the formula, go back to the fundamental counting principle. You are looking for first, second, and third places, which means you have 3 little cups to fill. You have 8 options for the first cup, 7 options for the second cup, and then 6 options for the third cup, which is the exact same thing as 336. So I hope with this example, you can see where the formula comes from. Now, you may have learned about permutations before, and now we're going to talk about something a little bit different, and this is a distinguishable permutation. And you use this when you have repeated elements. So let's go over how to find the number of distinguishable permutations, and then I'll show you an example and it'll all be clear. So suppose a set of n objects has n1 of one kind, n2 of a second kind, n3 of a third kind, so on and so forth. such that n equals n sub 1 plus n sub 2 plus dot 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 n sub k. And the number of distinguishable permutations of n objects is n factorial over n sub 1 factorial, n sub 2 factorial, dot 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 n sub k factorial. So now for that example, that'll hopefully make this clear for you. I want to know how many distinct ways can the letters in banana be arranged. So I have repeated letters. I have repeated A's and repeated N's. And if I swapped those two N's, it would be another permutation, but I couldn't distinguish it from the original banana, right? Or if I rearrange these A's so that the first A was in the back and the last A was in the middle and the middle A was in the front, it's still spelled banana. So I need a way to cut out those, in this case, repeated spellings. And that is to use this formula here for distinguishable permutations. So if I just permutate all of the letters in banana, I have 1, 2, 3, 4, 5, 6 letters in banana. So the ways to arrange the letters in banana is 6 factorial. But I have 3 A's. And there are numerous ways where I can put those A's that's not going to create a new distinct permutation. So I need to divide out the number of ways there are to place these A's. And there are 3 A's, and I have 3 options for which A goes there. I have 2 options for what A goes there, and 1 option for which A goes there, which gives me 3 factorial, or 6. Now I also have these 2 N's, and I have 2 slots to fill with N. I have 2 choices of N for the first one, and 1 choice of N for the second one, which means this is 2 factorial, and so then I get 60 distinguishable permutations of the word banana. Now, the contrast to the permutation is the combination, and in this case, order does not matter. And it's kind of weird that it's called combination, because when you get a lock and you have a combination for your lock or your locker, the order totally matters, but mathematically, a combination, the order does not matter. So this is more like finding the number of subsets as opposed to finding the distinct ways to arrange something. So if I just think about this case here, I want to find the number of 3-letter subsets of A, B, C, D, E where order isn't important. And if I figure out how many arrangements of A, B, C, D, E there are, well, that's 5 factorial total arrangements of all the letters. But that's not what I was asked. I was asked for 3-letter subsets. So I have 5 times 4 times 3 ways to arrange any 3 letters of A, B, C, D, and E, which gives me 60 arrangements. But this is where order matters. And inside this 60, I'm going to find the following subset: ABC, ACB, BCA, CBA, BAC, and CAB, that are just arrangements of A, B, and C. And I don't want to count these out separately. I want to count this as just one subset of the letters A, B, and C. And if I think about any 3 letters in this grouping, they're going to have this many arrangements, which happens to be 3 times 2 times 1, which is 3 factorial, or 6. So if I take this 60 and I divide out the 6, that's going to give me the number of combinations of 5 things chosen 3 at a time. So 5 times 4 times 3 over 3 factorial, 60 over 6, which gives me 10, right? So if order does not matter, I have to divide out cases like this, where I just have the same elements just repeated in a different order, because I don't care about the order. I just want to know that A, B, and C are together. It's like when I assign groups. I don't assign you a specific seat. I assign you a group to work in. I don't care which seat at the table you sit at, as long as you are with your group. So the procedure to find the number of combinations is to first find the number of permutations and divide by the number of ways to arrange each subset. Therefore, the number of combinations of n elements taken r at a time is written as NCR, which is the number of permutations of n elements divided by the ways there are to arrange those R elements, which is just R factorial. So if you plug in the permutation formula, you get this formula here, n factorial divided by n minus R factorial, R factorial. That thing there is a permutation. Add that R factorial, or the number of ways there are to arrange R elements, and then you get the number of combinations. And this should look totally familiar because this was also the way to find the coefficients in your binomial expansion. Surprise! So let's do a basic example, which could be useful if you ever become a poker player. How many 5-card poker hands can be formed from a standard 52-card deck? Well, once again, we don't care what order in which you get the cards, so order does not matter, which tells me that I have a combination. And I have 52 cards, and I have groups of 5. And so this is the calculation that I want to do. Now, if you forget the formula, you can do this, logically. You can think, well, I'm picking 5 cards from 52 and use my fundamental counting principle, which says I have 52 times 51 times 50 times 49 times 48, which is 5, right? This is the number of permutations. But then I have to go and divide out the number of ways there are to arrange those 5 cards, which is 5 factorial. And if I do some math and get a calculator, because I would not do this multiplication by hand, you're going to end up with 2,598,960 different 5-card poker hands from a standard single deck. Now, if you actually play poker in, say, a casino, they don't have just one deck of cards. They'll have a whole bunch of decks all shuffled together, which makes the number of hands much greater.